Okay, so now we are working with the idea of isomerism in alkenes. And if I look at the general definition for this, it says that these are compounds that have the same molecular formula but different structural formula. So what does this mean? So if I take a look at an example of, let's say I take methane, that is an alkane. Or I think let's take something like not methane. Let's take a butane. Yeah, let's take butane. So butane we know as C4H10. And if I draw the structure here, this we have studied is the structure of a butane molecule, right? And if I were to draw an isomer of this, so again, what is the definition says? It says the same molecular formula. And what is the molecular formula? This here is a molecular formula, but different structural formula. So this is the molecular formula, and this here is the structural formula. So the molecular formula remains same, but the structure differs. So if I were to draw an isomer for this, it's going to look something like this. And you'll have a CH3 here. Or if I draw with a little upward branch, this is something like this, a CH3. And why is this? Because this is how the isomer of a butane molecule looks like. Here you have something that we call a straight chain carbon. This is a straight carbon chain. This here is a straight carbon chain. And if I just draw it with a highlighter, you see this is something that we call as a straight chain. And this here, you see, now this is not a straight chain. And why is that? Because there is this branch popping out upward. So this cannot be called as a straight chain, right? Even if I have to show you like this, so let's say this is a straight chain. This is a straight chain, right? There's no point of break. There is nothing as a disruption or anything. But if you look at this one, this looks something like this. So of course there is a point of break here. There is a different route going upwards, or a different branch, going upwards. So this is something that we call the branched chain, a branch carbon chain. Okay, so now, these two here now are isomers of each other. These are both are isomers of butane. And because why? Because they have the same molecular formula. But if you look at their structures, they're entirely different. One is a straight chain and one is a branch chain. So this fits the definition. This satisfies the definition of the same molecular formula but different structures. Okay. And so you might think here, okay, the structure looks something like this. Now you can also have different ways to write this. You can also write in a different way. So there is one more way to write this, which is a bit more quick. So this is CH3, CH2, and this here represents a single bond. CH2 and again a CH3. This is a straight chain way of writing this, writing a butane molecule. Okay, if I were to write the same with the branch one, this would look something like this. So a CH3 bonded to a CH3 here as well, and you're gonna have, let's say we had a branch here, so this is going to look something like a CH3. Okay, so this is three hydrogens here, and a single hydrogen. So you can also write it this way. This is easier to write, just very quick to write. And yeah, so now you can also say, what if you had something like this? What if you had the carbon. Now we're just talking about the carbon chain here. The carbon chain in the butane molecule looked something like this. So we say this is a straight chain. But what if it was something like this? What if it was something like this? Or what if it was something like this? Now what? So again, if I try to highlight this, if I try to highlight this, and if I try to highlight it like this, and if I try to highlight this like this, and also like this. So what do you think? Is this a branch chain or this is a straight chain? And the answer to this is a straight chain. And the reason here is that because again, is there a point of break here? Or another way to understand this is that this carbon here, so the carbon at the last and the carbon at the start, both of these carbon are something that we call as a terminal carbon. And what that means is that these carbons are allowed to rotate. What does this mean? So for example, if this carbon stays here, this carbon, the last one, this can be, let me just make it real quick. This carbon, it can be here as well. It can be here as well. It can be anywhere it wants. It has that sort of authority. So is this carbon. So this carbon, which I have right now drawn here, this carbon can be here as well, and this carbon can be here as well. Similarly, in right now it is in this position, it can be here as well, and it can also be here as well. And the same goes for this carbon as well. These carbons, which is at the last and at the bottom, at the last and at the start, they have the authority to rotate in any position they like, and they can rotate. Okay, so this rotation doesn't mean that the molecule is now different. These are exactly the same molecules. Let me just draw it clearly again. So here, if you have like this, now this is a 3-carbon chain, but butane has 4 molecules. So 4 carbons. So now the last carbon, now that carbon can be here. Carbon can also be here, and that carbon can also be here. It can be anywhere it wants, and you can just highlight this to remember that this carbon has the authority to be anywhere it likes. And that doesn't change the fact that this is the same molecule as this one, as the first butane molecule. Alright? Okay, and even if you had something like this, even if you had something that looked like this, something that looked like this. Now again, if you notice, this is something that goes, that goes like this. And there is no point of break. Why? Because the carbon that are moving, which is this carbon and this carbon, if I were to draw these carbons in a straight chain, they would be like this, right? And the carbon that are moving are this one and this one. And that's what we see. Because these are terminal carbons, they have the authority to either move to any position they like. But within this spectrum, they can move here, they can be here, or they can be here, right? Like this. These are the 3 positions that they can take. The first one and the last one. And changing this, rotating this doesn't mean that this becomes a different structure. No, this is the same thing. This is the straight chain. Alright. So this is how the straight chain works. But now if I were to look at the branch chain, which was this one. So for this now this is the second isomer. This one is the first isomer, and this is the second isomer, right? And if I were to draw something like this, you might say, okay, CH3, CH3, and if I had the CH3 here, what then? Now, if you look at this molecule and if you look at this molecule, what would you say? Are these the same structures, or this is something different, or is this the third one is another isomer? And the answer is no. The third one is not any other isomer. This is the same structure, because you see this carbon, this CH3 is attached to the same carbon here. So it can be either at the top, it can be either at the bottom. It doesn't make any difference. Okay. So this is, again, these two are the same molecules. So what did we study? We studied that there are going to be 2 isomers of butane. And what are those? So isomers of butane are going to look something like this. One is this one, which looks something like this. And this is something that we call as the straight chain butane. What do we call this? We call this C4H10 straight chain butane, right? And the other one, the second isomer, looks something like this. Right? So this is a CH3. I think it will be better draw the full structure for this one. Yeah. So this, and you have 3 hydrogens here. You have a CH3 here, and this doesn't make sense. Sorry, this CH3 can be placed here as well. It is up to you. Where do you want to put it? Doesn't make any difference. Okay. So now, yeah. So this here, I'll draw the proper branch. So this is a C with an H, with an H here and an H here, and this is a CH3 as well. And you'll have one hydrogen here. Okay, so this is something. This is again a C4H10, and this is a branched chain, or we don't call that chain, branched carbon. You can say chain as well, branched chain butane, and the name for this is isobutane. We don't call this butane, we call this isobutane. And you might have one question here, which is that, okay, you might say that this is the main structure. How can this be an isomer itself? If this is the main structure, you're saying that there are 2 isomers of butane, and if this one is the main structure, how can this be an isomer? And that's a very valid question, because this makes sense. If something is a main structure, how can that thing be an isomer? So to answer that, you have to look at the definition again, or not the definition, but you have to look at this. This is a C4H10, what we call as butane. Now you need to keep in mind that what we are drawing here are different structures. Okay, it's just that this here is one way to draw butane, and this here is another way to draw butane. Okay, these are not, none of this is something that we call as the default structure, or something that we can call as that, okay, this is the main structure. No, we can draw butane any way we like. We can draw it this way, and we can draw it this way. Since there are 2 ways to draw butane, we call that there are 2 isomers of butane. Okay, makes sense? Perfect. Okay, so let's now look at the isomers of pentene, right? And this gets a bit interesting here, because previously we were dealing with how many? We're dealing with only 4 carbons, and now we are dealing with 5 carbons. So if I were to write the molecular formula, so this is the molecular formula, and if I were to write the structural formula, I'm not making the complete structural formula, I'm writing it this way: CH2 and a CH3. Now this, you should be able to recognize by now that this is a straight chain. This is a straight chain pentene structure, right? So this is the first isomer. Why? Because what did we say? That this is just, isomer is different. This is just a way of how we can write C5H12. We can write it this way. We can also write it in a branch format. The more number of ways we can draw the structure of a pentene molecule, the more number of isomers it has. So this is the first isomer. This is the first one. Now if I were to draw a branched one, so let's say this is a CH3 and a CH2, and where do I take this one? So okay, let's say I draw it on this one. Yeah, so this is a CH3. Now you have a branch, then you have a CH2, and then you have a CH3. You can also count the hydrogens. You've got 3 here, 2 here, 5, 8, 9, and 12. Make sense? Now this is a branch chain carbon molecule. Okay, so this is second isomer of butane. Why? Because now you have introduced a branch here, but we have to think, is there any other isomer of pentene that exists? So if I were to look at here at the straight chain, so let's say I draw something like CH3, CH2, 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 and a CH3. Would this count as an isomer? And the answer to this is no. Because why? If you look at this again, this is the same straight chain. There is no point of break. The carbon that we are using is a terminal carbon which has the ability to rotate. It can rotate anywhere it like. This is what we did in the last butane part as well. Okay, so this can rotate. So this is not a different isomer. This is the same structure. But if you look at the branched one now, if you look at the branched one, if I make something like this, let's say CH3, and then you have a C bonded to a CH3 and a C bonded to a CH3 at the bottom as well, and then you have a CH3 here as well. Okay, what if I draw this structure? Now this structure is indeed an isomer of butane. And why is that? This is the third isomer of pentane. Isomer of pentane. And why is that? Look, have a look at this. You've got one carbon here, one carbon here, one carbon here, one carbon here, and a carbon here. And you've got 3, 6, 9, 12 hydrogens. So you've got the same molecular formula. And you've got 12 hydrogens. So the same molecular formula, but the structures are different, which means that this is going to be what? This is going to be an isomer. Right? So this is one more way you can draw a pentane molecule. But what if you say here, okay, you can also ask that what if I place this one here? What if I place, what if I place this CH3 on this carbon instead of the second one? What then? So this is the place where we apply the concept of naming. So if you notice, in this molecule, you still have a 4 carbon straight chain. Even though this is a branched molecule, you still have a 4 carbon straight chain, right? And the way we name it is, the rule in chemistry says you always name from the carbon which is closest to the branch. Okay, and where's the branch? There is the branch. And the way you name it is like, this is 1, this is 2, this is 3, this is 4. Because why? Because we have named it from the branch, because we have named it from the carbon which is closest to the branch, right? If I were to name it from here, this would become 1, 2, 3, and 4. And there you have 3 and you have 2. So of course this is not the closest one, right? So since we have now named it, we can call this one 2-methyl propane. And don't worry, you won't be asked to name this. You would just be able, if you can remember this name, I think that would just work fine. Alright, but the main question was, what if the structure looked like this? Right, what if it looked like this? What if the branch was on this carbon? Okay, again the same rule applies. What did we say? We say we name from the carbon which is closest to the branch. And which one is closest to the branch? Now this one is the closest to the branch. So this is 1, this is 2, this is 3, and this is 4. So in the both molecules, you have the 2 here. Okay, so this is the second carbon here, and this is also the second carbon here, which means even if I place the CH3 here, or if I place it here, it makes no difference, because when it comes to naming, it's exactly the same molecule. So this is not a different isomer. This is the same molecule as the one we studied above. All right. So this is how the isomer of pentene works. So isomers in total have how many? They have three isomers of pentene. So one is the straight chain that looks something like this: CH3, CH2, CH2, and then you have one more CH2 and a CH3, right? So this is 3, 2, 7, 9, and 12. Yeah, that's perfect. And then you have one that looks like this: CH3. Then you have a CH attached to a CH3, right? If I'm not wrong, I have mentioned it correctly. Yeah, okay. You have a CH2 here and you have a CH3 here. So this is the second one. And the third one looks like this. So this is a CH3 bonded to a C with a CH3, and one CH3 is downwards, and you have a CH3 here as well. So these are the three isomers of pentane, and you'll be asked to have or to find out different isomers of different molecules, but these are kind of the one that sets the concept. So this is the end for this one. Okay. All right. Bye.